This is the notes for section 10.2, resonance, intensity, Doppler effect, and beats. So the first thing I'm going to do is go through the equations we're going to be using for this section. And the first ones we're going to go through the frequency of waves in a string or the waves of air or waves of sound in an open and closed pipe. So for a string, our equation is going to be F equals NV over 2L. And the variables will essentially be the same for all these, so I'll do them all first. For an open pipe, give me the same equation, F equals NV over 2L. For a closed pipe, though, I'll write that a little better. Our equation is going to be F equals NV over 4L. And F here is the frequency. Measured in hertz. N is the harmonic number. And assume that's 1 unless it specifies some otherwise. V is the velocity of the wave. And if it sounds for open and closed pipe, assume that V is equal to the speed of sound in air, which on average is about 340 meters per second. So unless it tells you something otherwise, assume that V is going to be 340 for open and closed pipes. And then L is the length of the pipe or the string. Alright, so those are our first three equations, and we'll just go on to the next slide here. So our next equation is the equation for the Doppler effect. And that equation is the frequency you hear, the original frequency, times speed of sound in air, plus the speed of the observer, over the speed of sound in air, minus the velocity of the source. And F, frequency you hear, and that's measured in hertz as well. F sub 0 is the original frequency, or the frequency that it would make if it was standing still. It's again measured in hertz. V is the speed of sound. And again, assume that is 340 unless otherwise specified. VO, speed of observer. This is meters per second. And VS, speed of source. In meters per second. And I'm going to shrink that down a little bit. And for VS and VO, they're both positive if moving toward, so if the source is moving toward the observer or the observer is moving away toward the source, they're positive, and negative if moving away. Right. And if one's moving towards and one's moving away, one will be positive and one will be negative. Right. last two equations, we have the frequency of beats equation and the intensity equation. So the frequency of beats you hear from two different frequencies of sound is going to be the absolute value of frequency 1 minus frequency 2. And so F beats is the beat frequency, frequency 1 and frequency 2 are just the two frequencies that are being heard. And last equation is intensity equals the power of the sound wave at the source divided by 4 pi times r squared, and r in this case is going to be the distance from the source. So I is intensity, and it's going to be measured in watts per meter squared. P is power, measured in watts, and r, distance from source. That's measured in meters. Alright, so those are our equations. Let's do the first 5 problems together. Number 1. What length of guitar string would vibrate at a fundamental frequency of 856 Hz if the string is stretched so that the velocity of waves in the string is 511 meters per second? So we have the frequency we're going to want to hear is 856 Hz. We know velocity of waves in the string is 511 meters per second. And we also know that it says fundamental frequency, and we see fundamental frequency, we know that n equals 1. So the equation we're going to use is F equals NV over 2L. And we're looking for L here. So you're going to say 856 equals 1 times 5. That's a terrible 5. Times 5, 11 meters per second, all over 2 times L. And we're going to multiply both sides by 2L, and then divide by 2 times 865, or 856 to find L. And we do that, we get L equals 0.30 meters. And that's our answer for L. Okay, next one, number 2. Number 2 says, what is the length of an open pipe in which the fifth harmonic has a frequency of 3,110 Hz? The speed of sound is 346 meters per second. So this ends up being the same equation since it's an open pipe. So F equals, or what we have, I guess, first is we have frequency equals 3,111 Hz. We have speed of sound is 346 meters per second in this case. Again, if it's not given, assume that's 340. And we have the fifth harmonic, so that's going to be n equals 5. So same equation, we'll be solving for the same thing as the length again. So the equation we're going to use is F equals NV over 2L. So we have 3,110 Hertz equals 5 times speed of sound in air, in this case, is 346 meters per second over 2 times L. And we solve that. In this case, we get L equals 0.28 meters. Alright, on to number 3. So number 3 says, what beat frequency is produced by two tuning forks that vibrate simultaneously with frequencies of 306 Hz and 310 Hz? So in this case, we have F1 equals 306 Hz, F2 equals 310 Hz, and we're looking for F beat, so the beat frequency. So the equation here is F beat equals absolute value of F1 minus F2. We substitute in there, we get 306 minus 310. I keep making brackets instead of absolute value signs. And see that math, we get -4, but again, since it's absolute value, we just get 4 seconds in between, or not 4 seconds in between the beats. The beat frequency is 4 hertz. So that's our answer. Number 4. Number 4 says the predominant frequency of a certain fire engine siren is 1600 hertz when at rest. What frequency do you detect if the fire engine moves at the speed of 10 meters per second toward you? So we know our original frequency. The original frequency is 1600 hertz. We know that the speed of the source, in this case, the fire engine, is 10 meters per second, and it's moving toward you, so that's going to be positive. And you're not given the observer is not given a velocity, so we'll assume that's 0 meters per second. And the speed of sound in air, since we're not given a value for it, we'll just assume it's 340 meters per second. So again, assume that the speed of sound in air is 340 if you're not given it. So we're going to use the equation, shrink this down a little bit. So again, we're given the equation we need to use, or looking for the frequency here. So the frequency, or the equation we're going to use is F equals F sub O times V plus speed of the observer, so speed of sound plus speed of the observer, over speed of sound minus speed of the source. So we have that equals 1600 hertz times 340 plus 0, get 4 a little better, all over 340 minus 10. We do that math, we get the frequency that is heard to be 1648 hertz. And that is higher pitched, and that's what we'd expect since the fire engine is moving toward us. And last problem we'll do together, and you'll do the rest on your own, is number 5. And number 5 says, the intensity of a sound wave is 9.1 times 10 to the negative 4th watts per meter squared at a distance of 7.3 meters. What is the power of the sound? So we're looking for the power that's being produced by the speaker, guitar, whatever it is in this case. So we have intensity equals 9.1 times 10 to the negative 4th, and that's in watts per meter squared. We have the distance R, distance from our source is going to be 7.3 meters, and we're looking for the power. So I'll shrink that down. So we're going to say intensity equals power over 4 pi r squared. So we get 9.1 times 10 to the negative 4th equals power, which is what we're looking for, over 4 pi times r squared, which is 7.3 meters. So we square that, and we solve that equation. We should get our power equals 0.011 watts. And that's the end. You guys should do the next ones on your own. And actually, let me double check the math on that one. And I'm glad I went back and checked the math on that, because this should be not 0.11 watts. When you do that math, you should get 0.61 watts. So that's our answer. Alright, so do the rest of the problems on your own. I'll be around to help you if you need it.